So I'm gonna present to you a very classical lecture about Monte-Carlo techniques. Okay. The main goal is to learn how to discretize stochastic processes, and then to apply these different techniques in order to compute European option prices. Okay. So before I'm gonna start by a reminder about simulation of random variables. This is the first part of my lecture. So first part is a reminder, simulation of a random variable. So first, Monte-Carlo technique. Monte-Carlo method is any technique allowing to compute numerical quantity using a random procedure. Okay, this is very simple. And the most popular one, one is based on the famous law of large numbers. Okay, which allows for approximations of the expectation of a random variable. This is the beginning of the story about Monte-Carlo methods. Okay, so let us recall briefly this first result. So one. We consider a sequence. So let xn be a sequence of independent and identically distributed in the following. I'm going to use the abbreviation IID, okay, the usual one. So independent and identically distributed random variables. Then we have the following convergence. X1 plus x capital N over N tends to the expectation of x1 as n tends to plus infinity, and this convergence holds almost short. Okay, this is a classical result. So this means that it is enough to simulate such a sequence of ID random variables to obtain approximations of the expectation of x1. Okay, so this means that it is enough to simulate a large number of ID random variables xn, and then approximate the expectation of x1 by the random variable m hat n equals, by definition, x1 plus x capital N of r. Okay? We need to be very careful about this random variable. What is the point space here? This is a set of all possible samples of size capital M. Okay? This is m hat n of omega equals x1 of omega plus xn of the same omega. And omega designates any possible sample whose size is given by capital M. Okay? This is the idea. So, in practice, we obtain such approximation by means of a software like MATLAB, Scilab, or directly programming a language like C++, for instance. Okay? So we're going to have the opportunity to learn how to use, for instance, Scilab, okay, to simulate the variables. So moreover, we have better results when the random variables xn appear to be in L2, that is our square integrable. Moreover, when xn belongs to L2, that is the expectation of x1 square is finite. We also have a convergence L2 as follows. So theorem. So 1, 2. So now I consider, let xn consider a sequence of RID random variables, RV for random variables. Such that the expectation of x1 square is finite. Okay? Then we get this estimate, expectation of m hat capital N minus expectation of x1 square equals precisely the variance of x1 over n. Of course, as you can see, as n tends to infinity, this means that the norm, or the difference between this random variable and the limit tends to 0. Okay. This is very important because actually this quantity also corresponds to the variance. So this means that if capital N is large enough, then the variance is very small. So that when you approximate the expectation of x1 by m hat n, you can expect with a large probability that most of the values taken by this random variable are concentrated around the mean. That is the expectation. Because of course the expectation of this random variable also equals the expectation of x1. Okay, this is the main idea. The proof is very simple. So just observe indeed that the expectation of m hat n minus the expectation of n1. This quantity just actually the variance of m hat n. That is the variance of 1 over capital N x1 plus x capital N. Okay. So, simplify this expression, 1 over n square, variance of the sum, and then now use the fact that the random variables are independent, so that the variance of the sum is the sum of the variance. So times sum of var of xi, and then you can conclude because all the variants are the same. Okay. So this is clear. Next proposition 13. So under the same conditions, that is, suppose that xn are id, and the expectation of x1 square is finite, then sigma hat capital N square defined as 1 over capital N minus 1, of course for n strictly greater than 1, times the sum for I equals 1 to capital N of xi minus m hat capital N square is an unbiased estimator of variance of x1, which means that first sigma hat n square tends to the variance of x1 almost surely as capital N tends to plus infinity. The first property means that sigma hat n square is indeed an estimator of the variance. And at last it is unbiased, means that the expectation of this estimator precisely equals a variance of x1. In particular, sigma hat n square over n is an abide estimator of variance of m hat n. We're gonna see that it is important to look after this estimation. The proof is also rather simple. You rewrite sigma hat n square as n over n minus 1 times 1 over capital N, okay, times the sum, and you split the sum as follows. That is xi minus expectation of xi plus, or x1 as you want usually, plus xi minus m hat n square, okay? So that you can split the sum in two parts when expanding this square, precisely n times n minus 1 times 1 over n, the sum for I equals 1 to capital N of xi minus expectation of x1 square plus 1 over n, the sum for I equal 1 to capital N of the expectation of m hat n minus m hat n square, because the expectation of m hat n is also equals to the expectation of x1 plus the double product sum for I equal 1 to n of xi minus the expectation of x1, okay, times expectation of m hat n minus x. Okay, now this is almost finished, because you can factorize this term by this common term, multiplier, okay, and then you compute this. But when you compute this, you observe here that it is just m hat n minus its expectation, but you need to be careful about the sign. Okay, there is an opposite sign here with respect to this term, so you get this term actually minus twice the same one, and then you get n over n minus 1 times 1 over n sum for I equals 1 to capital N of x I minus the expectation of x1 square minus 1 over n the sum for I equals 1 to n of expectation of m at n minus m at n square. Okay, but actually you can simplify. You can simplify this this term, because okay, all the terms are constant, and then you can forget this. So, okay, so you get here a very simple expression of the estimator. And then you can conclude, because first the random variables x1 minus expectation of x1, etc., x capital N minus expectation of xn, appearing in this sum. Precisely, I can consider the square of these random variables. and are of course IID. Because of x1, xn. Yes, so you apply the law of large numbers, and then you get this sum almost surely converged to the expectation of such random variable that is precisely the variance of x1. So 1 over capital N sum for I equals 1 to capital N of x I minus the expectation of xi square tends almost surely to variance of x1 as n tends to infinity. About the second term, term, we know that m hat n will surely converge to the expectation of m hat n, that is expectation of x1. Surely. Okay. So this second term tends to 0. So the conclusion follows. That is, sigma at n square tends to 1 times variance of x1. Now we may compute the expectation of sigma at n square, precisely n over n minus 1 times the expectation of this sum, which is precisely var of x1 minus the expectation of this term, which is just the variance actually of m hat n, we have already computed. That is n times n minus 1 times variance of x1 minus variance of x1 over n. This is the result we got in the previous proposition. Okay. And then you now understand why we actually divide here by n minus 1 instead of capital N, because we get this 1 minus, and this product equals 1. This is the reason. And of course, the last statement obviously holds, okay? Because when you compute sigma at n square over n minus actually variance of m at n, this is sigma at n square over n minus variance of x1 over n. So we know that sigma at n square tends to var of x1, so this tends to 0. Okay, and moreover, you can also compute the expectation of this term, and you exactly get the variance. Okay. So. We can now easily understand that the variance of the random variable m hat n is very important, and this is confirmed in the following result we know very well. So, I don't have very good maybe here. Yes. So, the variance of m hat n is of quite importance. Which is confirmed in the following. Okay, so this is the famous central limit theorem. Central limit theorem. So let xn be ID random variables in L2, such that the variance of x1 is strictly positive. Of course, otherwise it's a trivial case. Then the square root of capital N times the renormalized random variable m hat n minus its expectation, that is expectation of f1, over sigma hat n turns in low as capital N tends to infinity to n01, as you know, where n01 designates standard Gaussian distribution of which 0 and mean variance 1. Okay, that's a very well-known result. Moreover, probability that this quantity you consider it you take the absolute value, this quantity be greater than less than epsilon, converges as n tends to plus infinity to 1 minus alpha epsilon. So I fix strictly positive number epsilon. So this quantity tends to 1 minus alpha epsilon, where alpha epsilon is the probability that the absolute value of the standard Gaussian distribution greater than epsilon. This is not a surprise because we just use this property. That is as if we were replacing this random variable by its limit. Okay, but this is important to recall this property because in practice if capital N is large enough, we can claim that a known parameter, the expectation of x1 we want to estimate, okay, belongs to the confidence interval we deduce from from this inequality, that is m hat n minus epsilon sigma hat n over the square root of capital N, m hat n plus epsilon sigma hat n over square root of n. Okay, with a confidence level of 1 minus alpha epsilon. With confidence level of 1 minus alpha epsilon, or equivalently, the probability to be mistaken when claiming this property, that the expectation belongs to this interval, is less than alpha epsilon. Okay, this is the idea. So, now, of course, if we want to estimate this expectation, we need to compute such a random variable m hat n as well as sigma hat n. Okay, so this technique requires the simulation of IID random variables whose distribution is given. Okay? In practice, a computer cannot provide such a simulation, actually. A computer cannot provide random numbers, but generates what we call pseudo-random numbers. Pseudo-random numbers. So to do so, we use pseudo random numbers generator, pseudo random number generator, which is based on an algorithm. Okay, it's based on an algorithm. Which actually generates deterministic numbers. Based on algorithm. Generating deterministic numbers. For instance, we fix a large number, capital N distributed. Okay, so the relation between this capital N and the one in the previous theorems. And then we consider a sequence and consider a sequence. I consider a sequence UN, okay, such that UN plus 1 equals f of UN. F is some function. F some function from 0, 1, capital N minus 1 into 0, 1, N capital minus 1, okay? And a priori, U0 is given. Sometimes you may choose U0 thanks to the computer clock, for instance. And from there, we set xn equals un over n, so that you get some numbers in the interval 0, 1, for instance. Okay? What we want to choose f so that the sequence xn, okay, behave as uniformly distributed numbers on the interval 0, 1. Okay, this is the first step. So that the sequence xn behave as uniform numbers on the interval 0, 1. Random as uniform distributed random numbers on 0, 1. Precisely, this means that for every epsilon strictly positive, for every Borel set in B 0, 1, B of 0, 1, the sigma algebra, the Borel sigma algebra on 0, 1, we want the following, that is, there exists n naught in an integer, okay, such that for every n greater than n naught, the distance between the frequency of numbers xn belonging to A and the probability measure mu of A of the uniform distribution 0, 1 less than epsilon. Okay, so you want this quantity less than epsilon, that is the number of I such that xi belongs to A over the total number, capital N. So, of course, here I mean I less than N, such that xi belongs to A over capital N, the frequency, minus mu of A less than epsilon, where mu of A is a probability measure associated to the uniform distribution on the interval 0, 1. That is integral of over A of indicator function of 0, 1 of x dx. So this is a distribution of the uniform law on 0, 1. We denote by u of 0, 1 in the following this lecture. Okay. The most popular algorithm is to choose un plus 1 equals a times un plus b modulo capital N. Okay, very simple. That is, we choose f of x equals x plus b. And now we choose a and b with a, b such that the sequence u n is capital N periodic. Okay, actually this is not very difficult to find such constants a and b, and in the software like Scilab and MATLAB, they require that we have this property. First, b and capital N are relatively prime numbers, and secondly, I minus 1 is a multiple of any number dividing capital N. Actually, you can do, if you want, a very easy exercise. That is, just introduce Vn as un plus some alpha. Okay. Choose alpha so that Vn is geometrical sequence. Okay, it is a classical, just choose alpha so that you get the same relation with all b. Precisely, you get that Vn plus 1 equals a times Vn. And then, from there, you deduce an explicit expression of un, because you have such an explicit expression for Vn, because it is a geometrical sequence. Okay? And then from there you can solve u capital N plus k equals u n for every k. Actually, this relation, it appears that this relation does not depend on k, and then we can find a relation between a, b, and u0, so that this sequence is n-periodic. I'm not a specialist about the Borman numbers, but with a reference, if you want, a reference which is the following: Donald Knuss, the art of programming, of computer programming, volume 2, semi-numerical algorithms, third edition. Okay. For instance, about this algorithm, in MATLAB, capital N equals 2 power 31 minus 1, B equals 0, and A equals 7 power 5. Okay? And the corresponding code, which is what we are interested in actually, the corresponding code is the following: U equals rand, it's just for generating a random number u with low u of 0, 1, so very simple. And if you prefer to generate many independent random numbers, then you write capital M equals rand of m n, and then you get a matrix. M is a matrix with m rows and n columns. Okay? With of independent and a priori random numbers. Okay? According to the uniform distribution 0, 1. So you may interpret this matrix as a sample of size n times n. This is the idea. Okay? So this is a very simple code. This is important to do it. Okay? So in Scilab, actually, the code is the same because when I use Scilab, the code is the same. Just the constants change. It's here. Just for example, we have capital N equals 2 power 31, and A is more sophisticated. I can give you, but this is just for an illustration. And B is given by this so huge number. Okay? That's the idea. Just for you to understand the main ideas. Okay, so what we can following conclude is that we a priori know how to simulate uniform distributions thanks to computer. And so the second step is how to generally simulate more general distributions from this first step. Okay? So, if you are able to simulate uniform distribution of 0, 1, of course you can also simulate more general uniform distribution. And this is a very simple reminder because the uniform distribution on any interval AB where A is less than B is given by this formula, okay? B minus A U of 0, 1 plus B. Okay, so if you can simulate this, you can simulate this. Now, more generally, we can consider uniform distributions on a domain in Rd. Rd is a set of all d-dimensional vectors. So let us recall briefly the definition. A random variable x in Rd follows the uniform law on a domain D in Rd if its density function is given by f capital X of small x, x equals indicator function of x equals x1, x2, etc. over the integral over Rt of this same indicator function. Okay? In particular, if x1, xd are id with law u of 0, 1, that is a uniform distribution 0, 1, then you deduce that the vector x1, xd equals in law the uniform distribution on the product 0, 1 of that. Okay, so it's very simple. So now let us recall the inversion technique, which allows us to simulate general random variables from the standard uniform 1. So this is a so-called inversion technique. Proposition. So we consider x, let x be real valued random variable with cumulative density function CDF is a variation with cumulative density function f capital X of small x defined as the probability that capital X is less than x. Okay, So let us introduce the generalized inverse function. So let the generalized inverse function be fx minus 1 of y. By definition, this is the infimum of all y, x such that fx of x is greater or equal than y, and y belongs to 0, 1. Okay. Of course, if y equals 0, this is minus infinity. Because all x satisfies fx of x is positive. Okay. So, it's okay. So, if the result is the following, if the random variable capital U equals in law uniform distribution on the domain of fx minus 1, I will recall what the domain fx minus 1 is, then x equals in law fx minus 1 of u. And where domain, just the set of all y, such that this function is finite. Because you need it to compute this. Because you just want real value numbers. Okay? So, where domain of fx minus 1 equals the set of all y, such that fx, absolute value of fx minus 1 y is finite. Okay? Actually, this is the very classical result, but it is what we need to begin when we want to learn how to simulate random variables. The proof actually is very simple, because we just need to show that the two random variables have the same distribution, or equivalently the same cumulative density function. And then you can show that x less than x actually is no, it's fine. Yes, okay. Sorry. Fx minus 1 of u less than x is the same thing that that u less than fx of x. So we need to prove this, show this this equality. Okay. This equality actually is shown by showing the two inclusions. Okay. This is as if we could take in both sides the function fx. Okay. And then get u by fx. So that now the probability that fx minus 1u is less than x equals the probability that u is less than fx of x. You know that this number belongs to 0, 1, and u is an uniform distribution on 0, 1. So you know this quantity. This is the length of the interval 0 fx of x, precisely fx of x. And this means that a cumulative density function of the random variable fx minus 1 du, let's say is b, equals this one. This equality just means that the two random variables indeed are equal low. So this is the main idea. So this proposition is very important because this proposition, okay, gives a method to simulate any random variable if such that fx minus 1 is given, explicitly given. Okay? Indeed, simulate u and then compute fx minus 1 of u. Of course, a priori, u is restricted to the domain. So maybe you need to reject generally as a 0 or 1, but it's not very difficult. Okay? Actually, if you observe that this is 0, then you can easily reject it. Actually, we're gonna see the famous rejection method. Okay? How to reject some values. But you can also observe actually that you can maybe slightly modify this function in order for it to accept forbidden values of the domain, because the point is that u, for instance, equals 0 or 1 is 0, so this is not very important. Okay? But you need to be very careful when you write a programming code, actually. So, example, standard example, this is a case where the random variable admits discrete values. So example, exercise. So let x be a discrete random variable such that x of omega equals some xk, k greater than 1, with xk strictly less than xk plus 1 or k. And we denote pk, the probability that x equals xk. I suppose without loss of generality, but pk is exactly positive. Okay. So first question: compute fx and fx minus 1. So, to compute fx, just think of its graph, actually. What is the graph of fx? See something like that, where on the first axis you represent the possible values of x, right? Possible values of capital X, and then here you represent the probability that x less than x, that is fx of x. Right? So here what are these possible values? You know, just x1, x2, etc. So just for you to figure out all these things, x1, x2, etc. And then now it's very clear that if x is strictly less than x1, the probability equals 0. Right? And then from x1, between x1, you include x1 and you exclude x2, then in this first interval, if x belongs to this, x is less than x means that x equals x1, right? So you get directly on the value p1. And then you pursue the reasoning. For instance, here you get if x between x2 and strictly less than x3, okay, if x is strictly less than x3 but greater or equal than x2, then capital X is less than x means that x either equals x1 or x2. Yes? So the probability here is what is this probability?
Can you ask again the question?
I mean, when x between x2 and x3, what is fx of x?
X2.
It is a probability here.
X3.
No, here.
P1 plus P2.
Yes, P1 plus P2. Okay? Etc. And then you can pursue like this, so that you get a general expression. Actually, that depends where x is. Okay? So, first case, of course, finally, if x strictly less than x1, of course, fx of x equals 0. And then if x between some, say, xk and strictly less than xk plus 1, okay? So in this case, fx of x equal, what is the probability for capital X to be less than or equal to x? For x, it is possible if x takes values x1, x2, up to xk, right? So this is what you said, that is p1 plus p2 star plus pk. So we can write fx of x equals the sum of sum pi I equals 1 to k, right? Indicator function of the interval xk plus 1 of x for k equals 0, maybe infinite actually, like this. In this case, you just use the convention precisely that x not equals minus infinity, okay? And then the second one is the sum for I equals 1 to 0 equals 0. Right? Agree with this? This is exactly what I want before. Okay? So this is the expression. Now you can also use this graph to deduce fx minus 1. You agree with this expression?
Yeah.
Yes? I wrote otherwise this property. Now let us compute the generalized inverse of this function, that is fx minus 1. So, fx minus 1 of some y in the interval 0, 1. Okay? So, fx minus 1 of 0 is clear, this is minus infinity. I've already explained this. And now you consider some element y. For instance, we can start with an element y. Okay, you need to see y as an element of this axis. Okay, so you can first consider a case where y is positive and less than or equal to py. Okay, and in this case, recall that fx minus of y is the infimum of all x, such that fx of x is greater than or equal to y. So you need to observe the part of this graph which is above this line. Right? This is this part. And then you take the infimum value for x. So you get x1. This is the general idea. This y is strictly positive less than x1, fx minus 1 of y equals x. And you can guess easily the general expression. In general, if y strictly greater than x, okay, and less than x k plus 1, right? So follow this idea. Here, in general, you have xk plus 1, and then you have this graph. Here, you have the sum of pi for I equals 1 to k. So, sorry, there was a mistake here, of course. Here, this is we work on this axis. Okay. So, if y is between this value and the previous one, so for I equals 1 to k minus 1, imagine something like that, actually. And y is between the two values. Okay. Then, so for y between the sum of pi for I equals 1 to k minus 1 and the sum for I equals 1 to k of pi, then, sorry?
In the second line also p not x.
Yes, in this case, but this is okay.
Second
No.
line.
The second here? Line.
One line up.
Ah, this one, yes. Yes, sorry, you're right. This. Then fx minus 1 of y equals actually xk. Right? So from there you deduce a way to simulate such a random variable from uniformly distributed random variable on 0, 1. Yes? Here y is in this interval, and then you observe just the part of the graph which is below, above, sorry, this line. Okay? And you take the infimum, so xk. Okay? So,
So maybe you should write xk minus 1
Here?
Because of, no, yeah, because of the all different upper.
No, xk. Because y maybe is this sum, but y is strictly greater than. Okay? And then your line is strictly greater than this part. So you just keep the part from xk. So from there, deduce a technique, Monte-Carlo technique actually, to simulate x. Actually, this is very simple. Just applies the previous result, the inversion technique. That is, what do we need to do? We simulate U equals in low uniform distribution on 0, 1. And then x equals in low to fx minus 1 of u. Okay? We can rewrite as a sum of xk, indicator function of u belong between the sum from I equals 1 to k minus 1. Actually, I can, we don't mind about this strict inequality actually. And the sum for I equals 1 to k of pi, right? In general, as I told you, we may have a problem when computing this because of the domain of fx minus 1. But here there is no problem because the function fx minus 1 is well defined everywhere. Okay? And actually, of course, here there is also a convention because you start from k equals 1 to infinity. Okay, and then for x1, of course, convention, the sum for I equals 1 to 0 equals 0. Right? And then here you have this a priori. So now it is very easy to simulate such an environment, and we're going to have the opportunity to make some examples with Scilab. Okay. So now let us see another standard example. Which is the following. Give a way to simulate the random variable x equals in low exponential distribution of parameter lambda strictly positive. That is, we have fx of x, that is the density function of x, given by lambda exponential of minus lambda x, indicator function of x is positive. Okay. Actually, we apply the same method. You compute the solution. You compute fx of x, probability that x is an x, here as an integral from minus infinity to x of this density function. Okay? We need to be very careful, actually, when x is negative. When x is negative, because you integrate on r plus, okay? So when x is negative, fx of x equals 0. Otherwise, if x is positive, we can simplify this expression as the integral from y positive, okay, to x of lambda exponential minus lambda y dy, that you can explicitly compute this integral. Now it's easy. And then you get this function equals, you take the, of course, primitive, minus exponential of minus lambda y between 0 and x, right? And then you get 1 minus exponential of minus lambda x. So now you have an idea about this function, and we are seeking for its inverse, generalized inverse. So maybe it's convenient to see the graph of this cumulated density function. That is 0 here. And then now you present this function, okay? So the maximum, the supremum is 1, of course, okay? And then you present this function for x greater than 0, and you get something like this. A symptotic line here, and you get something like that, right? So, except the case where y equals 0, y equals 0, of course, fx minus 1 y 0 equals minus infinity. But otherwise, as soon as x, y is strictly positive, precisely here you have true inverse. Okay, fx minus 1 of y. Because you just keep the part of this graph which is above this line. You get this point. So you just need to solve, in this case, for y simply positive, you just need to solve 1 minus exponential minus lambda y equals what I am saying, okay, of x, okay, of x equals 4. And then you solve to find x. Okay, so it's really easy. Okay, and then you get this. So that fx minus 1 of y is given by minus 1 lambda logarithm of 1 minus 1. Okay, so in order to conclude, it suffices to simulate, to say that it's enough to simulate uniform distribution u on 0, 1, and then to compute this. But actually, you know that u of 0, 1 equals in law 1 minus u of 0, 1, which is very easy to get this result just by checking, or just intuitively. This is obvious, actually, by symmetry. So that to compute, to simulate x, you need to compute actually minus 1 over lambda logarithm of 1 minus u, but as 1 minus u still is a uniform distribution on 0, 1, it is enough to say that actually x, in this example, equals in law fx minus 1 of u, that is minus 1 over lambda logarithm of u, okay, u of 0, 1. You just need to be careful about the domain when you compute. You need to exclude 0, 1. But actually, there is another way. Either you reject by rejection method all the possible 0 values, but there is a simple way to do, actually. For instance, you can also claim that x minus 1 over lambda logarithm of u of 0, 1 almost surely equals to minus 1 lambda logarithm of some u of 0, 1, if you want, indicator function of u 0, 1 different from 0. I mean, you can change this function. Okay? You can change this function minus 1 over lambda logarithm, just modify it at the point 0, so that there is no more definition problems when computing through software. Because actually you know that the probability that the uniform distribution 0, 1 equals 0 is 0. So you don't mind. Okay? You don't mind. This is the main idea you need to keep in mind, actually. So now we're going to talk about the rejection method. In particular, the following rejection method allows us to simulate a uniform distribution on an arbitrary bounded domain. And this is very interesting because, as we have seen before, thanks to software, thanks to a computer, we may mainly simulate uniform distributions on some intervals A, B, and more generally products of such intervals. Okay? But if you need to simulate uniform distribution in a very sophisticated domain, then a priori it's also clear how to do. A priori. So we present this proposition, and then we're gonna see how to deduce the simulation of such uniform distribution in an arbitrary domain. So proposition 110. Let yn be a sequence of RID random variable that is independent and identically distributed with values in RD. Okay? Such that the probability that y1 belongs to some domain capital D is strictly positive, D is included in RD. Of course, we mainly work with Borrelian sets. The goal of this proposition is to propose a method to simulate the same law of y of this sequence, but conditionally to the fact that the real variables belong to capital T. So we introduce a sequence of random indices. Precisely, we set tau 1 the infimum of all k greater than 1, such that yk belongs to D. The idea is to only keep the values which belong to capital D. Okay? And then we inductively we define the next instant tau n plus 1, that is the infimum of all k strictly greater than tau n, such that yk belongs to capital T. Okay? We track all the indices such that the random variable, the associated random variable, belongs to the domain capital T. So now, we then define the sequence. The sequence then, the sequence x n defined as y of tau n satisfies the following properties. First, xn are IID, that is independent and identically distributed. And moreover, the probability that x1 belongs to some Borrelian set A equals the probability that y1 belongs to A, knowing that y1 belongs to D. Okay? The proof of this result is not so difficult, but it's always long to show because many calculus. It is not the goal of my lecture, actually, just a reminder. But I'm writing all my lecture on PDF files, so I intend to provide the proofs. Okay. In this PDF file. There is, moreover, interesting features about this scheme. Moreover, the expectation of tau1 equals the expectation of tau n plus 1 minus tau n equals 1 over alpha, where alpha is the probability for y1 to be in capital D. Okay, for every n. Actually, they are identically distributed, and observe that tau n plus 1 minus tau n is the time you need to get new value in capital D. Okay? New value for y, of course. And this result is important because this means that the smaller alpha is, the longer it takes time to simulate the sequence xn, right? But this is not surprising, of course, because it means that in some sense capital D is very small, so it is always difficult for the random variables y to take their values in capital T. This is the idea. From there, we deduce a corollary about how to simulate a more general uniform distribution. So, corollary. Let yn be a sequence of id random variable whose law is uniform distribution is u delta, uniform distribution on delta, which is of the following form. That is a product for I equals 1 to D of some intervals AI, BI. So this is a very simple domain. Okay? And then consider a more sophisticated bounded domain D included in delta. A Borel set in delta. Okay? So this condition holds as soon as actually capital D is bounded. So we set as previously tau 1 the infimum of all k such that y k belongs to D, etc. Tau n plus 1 the infimum of all k such that infimum of all k strictly greater than tau n such that yk belongs to D, and then the conclusion is that the sequence xn defined by y of tau n is iid and x1 equals in law to the uniform distribution on D. This is a very way to simulate such a distribution. Indeed, the proof is deduced from this, because if you apply this result, you get that the probability that x1 belongs to A equals the probability that y1 belongs to A, knowing that y1 belongs to D on the domain. And then we can rewrite this as the probability that y1 belongs to A and y1 belongs to D over P of y1 belongs to D. Of course, there is a slight assumption that is we suppose this probability is D, right? And then we can deduce the following, because this is one of the indicator function of a D of indicator function of a delta of x dx, but actually, okay, this probability, but this probability is just a little the same when you replace delta by D, because D is included in delta. So you can here just say this, and here you get the indicator function of actually D of x over A for the same reason. Because D is included in delta. Okay? So get this because D is included in delta. Right? A priori, you should write here indicator function D of x times indicator function of delta. Right? But we don't need to keep it. So, this is result. There is also interesting consequences of this rejection method. For instance, following corollary. So another corollary 112. Now we consider two density functions f and g. Let f and g be two density functions. Okay. Actually, the idea is to simulate a random variable whose density function is f, knowing that we are able to simulate a random variable with density function g. Okay, this is the idea. So we need to impose some conditions, in particular, such that f is less than some a g, where a is some constant, positive constant, a priori strictly positive constant. And of course, when I say that, actually, this implies that a is greater than 1. Because it just takes integral on both sides. Okay? So, now let sequence Zn of, let's say then, be a sequence of IID random variables with law U of 0, 1, the uniform distribution on 0, 1. No, sorry, not U, but afterwards. With law given by the density function, G, okay, and another sequence of IID random variables with low u of 0, 1, okay, independent of the first one, that is Zn. So this proposed technique supposes to simulate first this sequence Zn, and then you we then set the following sequence inspired by the rejection method, precisely tau 1 is the infimum of all k greater than 1, such that f of z k is strictly greater than a uk g of zk. So you can here imagine the corresponding domain in the rejection method. It's a kind of two-dimensional problem actually, because there is two variables, basically z and u. Okay, you can see this as a domain of all z u, so that the difference is positive. Okay, this is of the proof actually. And then, inductively, tau n plus 1 is the infimum of all k strictly greater than tau n, such that we have the same relation, that is f of zk is strictly greater than f uk g of z. From there, we still define the sequence xn as precisely z of tau n and we get that this one satisfies the following property. First, the xn are IID, and more interesting, actually, for n, the density function of xn equals f. Okay. So here we have a very simple way to simulate under this condition random variable whose density function is given by f. Okay. So we can see some examples. So first example. I don't know, example. So consider f of x equals 2 over pi square of 1 minus x2, indicator function of minus 1, 1 of x. This is why not? This is a density function. So here it suffices to choose. It suffices to choose g of x equals half indicator function of the interval minus 1, 1 x. Because it is enough to check that this relation holds. We see here a equals 1. No. 4 over pi. Okay? So very simple. Another example, exercise if you want. Exercise. Consider f of x equals lambda over 1 minus exponential of minus 2 lambda, exponential of minus lambda x, indicator function of 0, 2 of x. And then try to find g as well as a. Okay. So now, for the end of this first chapter, we recall the change of variable formula. Because this gives us also a way, method, a Monte-Carlo method to simulate unknown variables. Okay? So, lemma 114. Let psi be a diffeomorphism. I mean by this one-to-one correspondence, which is differentiable as well as its inverse. Okay, so you, psi minus 1 exists, the inverse function, and then you can differentiate it. So we can consider psi as a mapping from some delta 1, including RT, into some delta 2 in RT, where delta 1, delta 2 are open set. Actually, it is enough to consider open sets because you're gonna direct functions, and so you can exclude the boundary of the sets in the case where they are closed, for instance, when you work with Lebesgue measure. So we have this change of formula, change of variable formula, which is very well done. That is good to remind. For every bounded Borel function g, the integral on delta 2 of g of y dy equals, now to get the formula, we imagine that y equals, because psi takes its values on delta 2, and this is actually a rejection, then you can imagine that y is some psi of x. Okay, this is a change of formula. The change of the variable is actually given by y equals psi of x. Okay? For every y in delta 2 there exists unique x, that you have this by assumption. That you can rewrite it as integral on delta 1 of j of psi of x first, and now you need to differentiate this, and so you get precisely the determinant of the gradient of psi x dx. Okay, so this is very well done. But this is an important result because from there you get the following corollary. 1.15. Let x be a random variable with values in an open set delta 1 in RD, and of density function fx. Now consider psi be a diffeomorphism okay, from delta 1 to delta 2. Then we can give the explicit density function of the image of this random variable x by psi, precisely. Then y equals psi of x, okay, admits the density function fy equals determinant of gradient of psi minus 1 times the f of psi minus 1, indicator function of delta 2. You know this notation?
Compose function.
Yes, compose function. Okay, f of psi minus 1. Actually, the proof is not very difficult. You just need to, so you can do it by yourself. Proof, just compute the probability that y belongs to some a, right? And then you make a change of random variable because it is integration, the following thing. This is the indicator function of expectation of indicator function of psi x belongs to a, right? So you can just see it as an integral of indicator function of psi x belongs to a times the density function of fx, dx. And now you change the things that here you get y. So you change the variable is psi of x equals y. But actually, be careful, it is not the same, exactly the same that I wrote here, because here I start from this to get this one, and then the change variable was more from y to x, okay? And then here you should better see this like x equals psi minus 1 of 1. And this is what you see this. So now you can pursue the proof. Okay? This is a very interesting result because from there we get the famous Bucks-Müller method. Okay, so application. The box Müller method, which is derived from this corollary. Okay, precisely. Let U1, U2 equals in law some uniform distribution on the product 0, 1 square. Okay, we know how to simulate this. This suffices actually to simulate two independent uniform distributions on 0, 1. we have already mentioned in the beginning of this lecture. So this is very easy. Then we define x1 precisely the square root of minus 2 logarithm of u1. Of course, I need to be very careful. Maybe I'm not very precise. Here, a priori, we need to exclude 0. Okay? Times cosinus of 2 pi times u2. One u2 has 2 components of these two-dimensional random variables, and x2 equals square of minus 2 logarithm of u1 times the sinus of 2 pi u2. Okay? Then x equals x1, x2 is such that it is equal in law to Gaussian distribution, a two-dimensional Gaussian distribution 0, I2. I2 is the identity matrix in the two-dimensional case. Precisely, I2 equals 1, 0, 0. So this means in particular, this Gaussian case that the two random variables x1 and x2 are independent. Okay? So it is a way to get Gaussian distribution, to simulate Gaussian distribution actually. Also that this result is an immediate consequence, immediate when doing the calculus actually, because you can see x as the image of this initial random distribution. So mapping psi, you can identify through these two equalities, right? So now I just compute the corresponding gradient, etc., and then you get this. Okay, so this is an important result, and in particular, this method is used in Scilab software we're going to use from, of course, from RAND. RAND, this is a code we use to simulate uniform distributions. Okay? So this is the idea. At last, for today, it is the end of this first lecture actually. I think I'm going to start the second part tomorrow about different processes. Okay? So it is almost the end, just 5 minutes. So about the correlated random variables. Okay. So let xy be a random variable with a density function f of x1. Okay. The density function of y, knowing that x equals some value small x, is given by such function I call f of y, knowing capital X equals small x, and satisfies certainly you know, f of xy equals f of x, right, times this conditional density function, obviously, f of y, knowing x equals x, right? So that from there it is very easy to simulate such a random variable. Indeed, therefore, it is enough to simulate x of density function fx. So you know how to do, because there are many techniques to do it, as we have seen before, and then simulate a random variable z with density function f of z knowing x equals x star, where x star is the observed simulated value of x. Okay? So finally, to simulate such a random variable, it's enough to know how to simulate a real value random variable whose density function is known. This is very clear. Okay? So this is the end for today. Thank you.
Thanks.